Welcome to this explainer. Today, we're literally stepping onto a microscopic battlefield. We're going to be exploring modern semiconductor manufacturing, which, if you think about it, is an arena where engineers are locked in this epic, daily battle against the fundamental laws of physics. We are talking about structures so unimaginably small that just a few misplaced atoms can derail an entire piece of technology. If you've ever wondered how the chips powering your phone, your computer, or advanced AI actually work down at the atomic level, well, you are definitely in the right place. Today, we're actually going to decode the exact training slides used to teach advanced semiconductor technicians. Specifically, we're pulling this right from a Module 2 presentation. So let's jump in. Okay, just to make sure we don't get lost in the weeds today, here is our roadmap. We're going to cover the core building blocks, how logic is going 3D, the interconnect bottleneck, and finally, wrap up with the chiplet revolution. All right, starting with Section 1, the core building blocks, defining the priorities. Before we can even begin to understand these complex systems, we really need to meet the primary characters of our chip design story. So right off the bat, we have a fundamental battle of priorities here. First up, we have logic devices. I want you to think of these as the sprinters of the semiconductor world. Their absolute number one priority is speed. We need incredibly fast switching and precise control over voltage to minimize what we call RC delay. That's resistance and capacitance delay. Every single fraction of a nanosecond absolutely counts for logic. Now, contrast that with memory devices. If logic devices are sprinters, memory devices are more like massive cargo ships. Their ultimate superpower is density. The entire goal here is to cram the absolute maximum number of bits into the smallest possible physical area. And to do that, they have to rely heavily on 3D vertical stacking. So because they have these totally different engineering goals, speed versus density, they end up looking and behaving completely differently at the microscopic level. But of course, as we try to make both of these types of devices smaller and smaller to keep Moore's law going, we slam right into some major microscopic roadblocks. The biggest villain here, without a doubt, is leakage current. Imagine you're trying to shut off a tiny water valve, right? But the water just keeps dripping, no matter how hard you turn the handle. That is exactly what happens when we shrink transistors too far. We encounter something called subthreshold leakage. This is when current just keeps flowing even when the gate voltage is completely below the required threshold to turn it on. And the kicker? It gets exponentially worse as that gate length gets shorter. And if that wasn't enough, then we have GIDL. That stands for gate-induced drain leakage. Because the electric fields are so incredibly intense in these tiny microscopic spaces, electrons actually tunnel right through the barriers. We are talking literal band-to-band tunneling here. It's crazy. These leakage issues became such a nightmare that they basically forced engineers to stop shrinking things flat on a surface and find a radical new way forward. Which brings us to Section 2, going 3D, logic architectures, or escaping the planar trap. To solve those massive leakage problems we just talked about, the industry had to completely rethink its geometry and take logic designs upwards into the third dimension. For years now, the industry standard has been the FinFET. It's a 3D tri-gate transistor, and honestly, it totally revolutionized the field. But here's the thing. As we push down into the sub-3 nanometer nodes, even FinFET is running out of steam, which raises a really critical question for the industry. Why do we desperately need a new architecture called Gate-All-Around, or GAA? Well, the answer lies right here in Gate-All-Around. And honestly, it is exactly what it sounds like. It's a nanosheet architecture where the gate material actually wraps completely around the silicon channel on all four sides. Think back to that leaky water valve analogy we used earlier. If FinFET is basically like putting your thumb over the end of a running hose, GAA is like clamping a heavy-duty vise tightly around the entire circumference of the pipe. This brilliant 3D structure gives engineers truly superior electrostatic control over the channel, and that is exactly what successfully suppresses that problematic off-state leakage we were just talking about. So there is a very exact trade-off at play here between the two. With legacy FinFET, if you need more drive current for performance, you literally have to add more physical fins side by side on the chip. That eats up precious real estate and totally limits your overall density. But with GAA, it's a game changer. You can adjust the width of the channel simply by changing the thickness of those nanosheets stacked on top of each other. What that means for designers is that you get a much higher drive current for the exact same footprint on the chip. It is basically the ultimate space-saving maneuver to mitigate those short channel effects, and it's exactly why GAA is taking the crown at the absolute cutting edge of manufacturing right now. Now, let's pivot to Section 3, the skyscraper, 3D NAND building upwards for memory. Because while logic devices are really just starting to embrace these complex vertical nanosheets, memory devices, They have been building true microscopic skyscrapers for years now.
167. I really want you to just let that number sink in for a second. When we talk about 3D manned memory today, we aren't just talking about, 3 or 4 stacked layers. Modern manufacturing allows us to stack 176 layers, and honestly, even more than that now, right on top of one another just to store data. It is a staggering, almost unbelievable feat of architectural engineering, and the craziest part is, it's all happening at a scale completely invisible to the naked eye.
So, you're probably wondering, how do you actually build a 176-story microscopic skyscraper? Well, it requires a pretty mind-blowing sequential process flow. First up, you do tier stacking. This means depositing alternating pairs of oxide and nitride over 100 times in a row. Next, you perform a staircase etch. You are literally cutting microscopic steps into the sides of this stack, so you can eventually connect wires to all the different specific levels. But step 3, that's the most critical one, the channel hole. You have to etch a perfectly straight vertical hole right through all 176 of those layers. We are talking about an aspect ratio of over 40:1. If that hole bows or twists even slightly during the etch, the entire memory cell fails. Then, step 4, you fill that hole to create a vertical polysilicon channel. Engineers often call this the macaroni structure because of how it looks. Finally, step 5, you etch out all that nitride you put down earlier and replace it with conductive metal to form the word lines. It is an incredibly stunning, complex cycle of deposition and etching. But here is the secret. Absolutely none of that crazy skyscraper construction would be possible without a fundamental shift in how we actually store the charge itself. Legacy memory used something called a floating gate, but when they tried scaling that below 20 nanometers, the charge just started leaking between the adjacent gates. It was a mess. The brilliant solution was charge trap flash, or CTF. Instead of a conductive layer where the charge moves around freely, CTF uses insulating silicon nitride to create discrete, localized charge traps. Because the charge is trapped and can't freely flow, it doesn't leak over to its neighbors. And that right there is the secret sauce that enables this massive vertical stacking. Moving right along to section 4, the interconnect bottleneck, beating the RC delay. Because at the end of the day, all of that incredible speed and density we just talked about is totally useless if the electrical signals can't actually travel between the transistors efficiently. So the crucial point to understand here is this. As we hit those sub-5 nanometer nodes, the tiny copper wires up in the standard back-end of line, or BEOL, simply became too resistive. It essentially created massive signal traffic jams across the chip. This is that dreaded RC delay, resistance times capacitance I mentioned earlier. To fix this, engineers actually had to invent an entirely new intermediate layer called the middle end of line, or MEOL. This MEOL layer sits directly over the active transistor areas to provide ultra-low resistance local interconnects. Think of it like they built a high-speed carpool lane that completely bypasses the congested, higher-level metal traffic, saving the entire chip from crippling signal delay. All right, bringing us to section 5, the chiplet revolution, disaggregating the SoC. Let's completely zoom out from the individual transistors and tiny wires for a minute and look at a massive paradigm shift happening in how we package these entire systems together. Historically, the industry always built monolithic system on chips, right? You put everything, the logic, the memory, the I/O, on one massive single silicon die. The problem with that? Well, a really large area means you have a much, much higher probability of microscopic defects ruining the entire extremely expensive chip. The modern solution is disaggregation, better known as chiplets. Instead of building one giant chip, you build a team of specialists. You break the system apart into smaller, highly specialized dies. Smaller dies automatically mean you get a higher manufacturing yield. But even better, you can mix and match your technology nodes. You can use a super expensive, cutting-edge 3-nanometer node for your core logic, but then use an older, much cheaper node for basic I/O functions and stitch them all together in one seamless package. Now, once you break a chip apart like that, engineers face some really complex trade-offs when choosing an integration base to put them back together. If you need ultra-high bandwidth, say you're connecting high-speed logic directly to stacked memory, you're going to use a silicone interposer. It gives you incredible routing density with trace lines under 1 micrometer, and it uses through silicon vias, or TSVs, for the vertical connections. But it's very expensive. On the flip side, if your bandwidth needs are a bit lower, you might opt for an organic substrate. It's significantly cheaper, but you're trading off routing density. It's much lower, and you have to use standard plated through holes instead. So it's this constant, delicate balancing act between maximum performance and total cost. But when we want the absolute tightest connections possible between stacked chiplets, we use something that is honestly straight out of sci-fi: 3D hybrid bonding. Unlike older methods, this uses absolutely no solder or micro bumps whatsoever. None. It is a direct copper-to-copper thermocompression interconnect. We are talking about a bond pitch of just 1 to 10 micrometers. This provides the absolute lowest resistance and the highest input/output density physically possible. But the catch? It requires extreme surface planarization. The two surfaces have to be polished so perfectly, flawlessly smooth, that when they finally touch, they essentially fuse together at the atomic level. It's wild. So what does this all mean? Well, for decades, Moore's law, this idea of continuously geometrically shrinking transistors, drove absolutely everything in tech. But as the entire industry evolves, this new era of more than more represents a massive shift. We are moving from simple geometric scaling to complex system-level integration. It's no longer just about making things smaller, it's about how smartly we can stitch together GAA logic, 176-layer 3D NAND skyscrapers, and specialized chiplets using advanced packaging to just keep pushing performance forward. Which leaves us with this final, provocative thought for today. We've wrapped our gates on all four sides, we've built massive memory towers, and we've literally broken our chips apart just to bond them back together atomically. But the global demand for computing power, it never stops. As we push beyond 3 nanometers, fully into the angstrom era, what new laws of physics will stand in our way? And what radical new architectures will we have to invent to conquer them next? Thank you so much for joining me on this deep dive into Module 2 today. Stay curious, keep learning, and I'll catch you on the next explainer.